Welcome. This is a new type of webinar that we're doing, which is a guest speakers sort of situation. Thanks so much to Kamran and Trevor for agreeing to help us out here. Um, Kamran is a grad student um, at Stanford who's been doing a lot of work with PIPSA, which is a energy modeling framework. There's a whole bio that you probably were able to read, so I'm not going to read it out loud because I always find it kind of annoying when people do that. Um, and you'll learn a lot about his work shortly. Similarly, Trevor is also a grad student who's been doing a ton of work with the modeling uh, frameworks. Excuse me. Um, and they've been working together with Pipes at work. And he's gonna present on his work as well. Um, sorry, a little frazzled. But yeah, you'll both be presenting. You have your own presentations. Which one of you wants to go first?
I will start off and then Trevor's going to join afterwards. So,
Great. And I'm really looking forward to learning more about your work because it's exciting that Puddle feeds into it, and I don't really understand it. So I'll be excited
yeah.
to get to know a little more about it.
Yeah, happy to share. Um, I'll get started here.
All right.
Let me know if my screen
Yeah.
is coming through correctly.
Yeah. And if anyone has questions, just pop them in the chat. And probably I'll try to do some chat management, and then at the end you can see what you got, Gavin.
All right, thanks everyone for joining. My name's Kamran, as Dajong said. I'm going to present on Pipes USA, a flexible and open source electricity system planning model for the United States. This is work that's done in collaboration with Trevor Barnes, a PhD student at Simon Fraser University, and it's supported by my group, the Interdisciplinary Energy Systems Research Group at Stanford, and the Bits and Watts Initiative, as well as Trevor's home university, Simon Fraser University in Canada. So thanks so much for joining, and I'll get started. So electricity system planning is a very difficult challenge we have ahead of us in the coming years. Um, System planners have to deal with things like demand growth from data centers and electric vehicles in the future, and heat pumps and other forms of electrification coming up. There's extreme weather events that cause peaks in demand over heat waves, as well as events like the winter storm Uri in Texas, which dramatically cause power outages and loss of life. There's also a strong drive for renewables and the associated infrastructure that you need to integrate those renewables. So think transmission lines, as well as battery energy storage. And all the while, there's retiring coal plants, retiring natural gas plants that make this problem even more challenging. So this is a big problem. System planners are dealing with a myriad of issues at the intersection of these three challenges and more. And all the while, they need to make sure that the system is reliable, so the lights have to stay on, and affordable. We can't have costs skyrocket above how much they already are. So if this problem isn't tough enough, our system planners aren't all sitting next to each other eating lunch every day around a table. They are an assortment of different actors. So there's load serving entities, LSCs. So these are your think of your home utility that you probably hear about by name most often. There's independent system operators, ISOs. These are the transmission planners. There's also public utilities commissions that are involved in the planning process, setting policies. And each of these different stakeholders or planners have used models of different spatial, temporal, and operational resolution. So the planning problem that LSC is solving is different than the planning problem that the ISO has, and they have different objectives and different constraints within each planning problem. And so, what are what this model is designed to do is to help this planning issue, address this planning issue, to be able to flexibly move between these different spatial resolutions. So. Um, starting off with the spatial resolution, when I was starting off with my research, I started looking at the existing models in the literature. On the top are three common or well-known planning models of the United States, which is a model that has a US portion that is based on power genome, but it also has its own WEC, Western US model. It has 44 nodes for the WEC. The power genome model, which is used in primarily Gen X, but also has been used in a couple other models for the model under comparison project, has 60 some nodes for the US, and the Reed's model has 134 nodes for the US. So these are all really great models that have about appropriate spatial resolution for modeling the entire US or large swaths of the US. But when we want to zoom in on a particular region, for example, if you were just planning for California, it's often the case that, for example, 4 nodes for California, as used in the Reed's model, isn't enough to capture the internal transmission constraints that exist within California. And so this is really what motivated us starting working on this problem. And so we found work that had been started actually at Tom Brown's group, the folks who made PIPESA, that used the Texas A&M Breakthrough Energy Network model that they used to cluster the network to make it a smaller spatial, lower spatial resolution, sorry, finer spatial resolution to be used for capturing these transmission constraints. So I'll talk a little bit more about that first, but let me tell you, Pipes USA is a data model and optimization tool with flexible transmission resolution and broad temporal scope. So here I'm showing you a list of a graphic of all the data sources that go into PIPESA. And through this presentation, I'll walk through some of the important ones to give you a better picture of sort of what are the features of the model and what data you can use to build your energy systems models. So first, I want to start off by saying the data model is not the optimization model. So the data model is is used to parameterize the optimization model. So the optimization model in energy systems and electricity systems modeling are the set of constraints that you use to define, for example, transmission constraints or operational constraints, such as unit commitment, ramping rates, and so forth. All of that requires a separate data model that needs to be flexible to scale up and down in different dimensions of resolution. So just to throw some household names out there to give you a picture of where Pipes USA fits in this framework. Pipes USA is the data model, which we use PIPESA to solve our optimization model. Similarly, you can think of Power Genome as the package that produces the data for Gen X, Tomo and Switch potentially. Sienna data is a similar package that produces the parameters that are used in Sienna ops. And I put NREL reads at the top there because it's kind of one package that has the data model living in a bunch of living separately, I guess, together with the optimization model within one software. So what I mean by flexibility in time and space is that when we're conducting energy systems models in the spatial dimension on the left, you'll see on the far left, you'll see a graphic of a network that has full resolution, which we can cluster individual devices separately from transmission lines. So in that middle panel, you'll see we cluster transmission lines between regions, and on the furthest right panel, we cluster both the devices within a region as well as the transmission lines. Similarly, in the temporal dimension, there's different methods to use time slices or some clustering or resampling method or modeling full chronology. Likewise, you have control over the model scope, so single horizon problems or multi-horizon problems solved sequentially or with perfect foresight. So where did this get started? This was a project actually started by Tom Brown's group. I saw he was on the call. Nice to meet you, Tom. I've read all your papers. Um, Tom Brown's group, Fabian and Martha, had started this project by clustering the Texas A&M network into a finer nodal resolution using there's multiple clustering algorithms, but essentially clustering algorithms to reduce that network size from something that is not really computationally feasible to solve with 87,000 nodes for the United States into one that you can scale flexibly depending on the question you have at hand. So um, this is one of the transmission networks available in Pipes USA. What we found was that this transmission network, the Breakthrough Energy Network, is synthetic, and if you were to zoom into particular parts of the United States, you would realize that the transmission capacity doesn't really closely represent reality. So um, Pipes USA is also has three other transmission networks that you can use instead, and these are the nearest. These are derived from the nearest nodal network. So the nearest nodal network is non-public. It's CII protected data that the national labs have access to, but um, thankfully, NREL, the National Renewable Energy Lab, has published zonal interface limits that are derived from the nearest nodal network. And they use an optimization method to calculate these zonal limits by essentially maximizing the amount of power that can flow from region 1 to region 2, subject to n-1 constraints. And they publish these networks at three different spatial scales. So there's the classic Reed's network, which you can think of as almost a balancing area resolution network, as well as a county level network that has 3,000 some hundred nodes, as well as a FERC Order 1000 transmission planning region network with 18 zones. So these networks are zonal, so they don't use they don't have DC the information necessarily for modeling DC power flow and transmission, but they are I would say a high quality representation of the US's transmission system. So we implement these three networks and also a feature where you can mesh these networks. So for example, I'll show you some example networks in the US. Here we have the WEC on the left and ERCOT is Texas on the right. The WEC network I'm showing on the left panel is represented at balancing authority or Reed's network resolution. And the second one is with California represented at a county level resolution. So meshing between the county level resolution of the nearest derived network and the balancing authority level resolution, which I have found useful in modeling when I want to study specific transmission constrained resources within California, for example, offshore wind in Northern California. And on the right, I have a similar comparison with ERCOT, the 7-node network that's commonly used in Reeds compared to an 182-node network at county level resolution. So in addition to the 4 different transmission networks, we use the AtLight tool, also developed by the Pipes of folks to integrate over 80 years of historical climate data from ERA 5. This is done with a 30-kilometer grid cell resolution for the US with over 4,000 nodes across the US. And it has hourly resolution for each of those years. We are soon to release a secondary climate data set that you can use that has climate change informed data on weather, climate variables, as well as capacity factors for different renewable resources. So keep an eye out for that. And so on top of that, we include individual estimates of renewable renewable capacity potentials for each region in the U.S. using land satellite information, data on federally protected areas, bathymetry, um, and also regional specific land screens. For example, in California, the CEC, the California Energy Commission, produces a really nice data set on where solar and wind can be produced. We also have data sets from both the Bureau of Ocean Energy Management for offshore wind and a couple others as well. So where does Puddle come in? Puddle is used primarily in the generator data. So all the EIA 860, the EIA, sorry, the NREL ATB, the EIA Annual Energy Outlook. So all the data on existing generator capacities and fuel receipts data has been really nice to get from Puddle. We integrate that as well. So in addition to the Puddle data, we also like to supplement some record linkages we've done from the WEX planning data set, the ADS anchor data set, as well as we interface directly with the CAISO's Oasis platform to pull daily natural gas fuel prices for different fuel regions across the US. So you have a lot of control over if you want to run a historical simulation, I can get actual fuel prices for the West Coast and monthly fuel receipts at a unit level for existing thermal generators. And demand data. So like I mentioned, you can run historical simulations. So we have historical data coming from the grid emissions EIA 930 data set at a balancing area scale. For right now, we have 5 historical weather years, and we also have demand forecast from the NREL Electrification Future Study at the state resolution with hourly resolution going out to 2030, 2040, and 2050. So for those who aren't immersed in the electricity system modeling space, I threw in a slide just to show you what the formal formulation of a capacity expansion model is. We are when we model these problems, we're seeking to minimize the operations cost and annualized investment cost, subject to constraints such as generator operating limits, land use constraints, storage, power and energy constraints, transmission limits, power balance, and as well also policy constraints. So in the US, one very important aspect of our modeling work is the inclusion of regional policy constraints. So California has aggressive emissions targets, as well as there's other RPS standards that are diverse by each state across the United States, as well as capacity targets on specific laws that have passed that might state something like X amount of coal capacity must retire by a certain date. All of these regional policy constraints are included in the model, and the way we handle this is through integration with the NREL READS model. So since we use these READS networks, we also import the regional policy data from those networks as well. And so I'll just show you some quick example of some results from running the model. I'll give you 2 case studies, one on just nationwide transmission expansion. So I present 2 cases where I'm examining the role of transmission expansion in reducing system cost and impacts on investment decisions. So on the bottom x-axis, you'll see transmission expansion factor. This is the factor above which today's transmission system is allowed to expand. So 2 is equal to a doubling of transmission capacity as measured by megawatt miles. And the business as usual scenarios, just including current federal and state policies, and the zero emission scenario is a zero emissions case for the entire United States. So what we see is that intuitively, zero emission scenarios are more expensive. We have to build a lot more variable renewable resources. However, if we are able to expand transmission, we're able to greatly reduce these system costs. So we see that as we expand more transmission, there's a lot more onshore wind that's being developed. And we have a reduction in, for example, nuclear in the zero emissions case. Also, you'll notice that the black line, which is system cost, is much steeper in the zero emissions case. So there's a lot more benefit to this transmission expansion in zero emission scenarios. And just to show you visually what this looks like in the United States, I'm using the Reeds network for this example with 8760 hourly resolution. We're building a ton more offshore wind in the center of the country and needing to transmit this to the coasts or demand centers. Another application, as I mentioned earlier, transmission resolution is really important in California, where there's transmission constrained offshore wind. If you look on the figure on the right, the Humboldt call area is in Northern California, has really great offshore wind resource and was one of the BOEM call areas. However, there isn't much transmission capacity going to that part of California. And so the CEC, the California Energy Commission, has set really aggressive goals for offshore wind to integrate 25 gigawatts by 2045 and 5 gigawatts by 2030. The CPUC, the regulatory commission in California, has even approved a central procurement entity to be able to that is able to procure up to 7.6 gigawatts of offshore wind. So they've really set strong goals and even shown that they're willing to take on some of the risk internally for this resource. And so to look at some of the modeling that is being conducted, on the left, you'll see the capacity expansion model from Reeds, which is the model that the state uses to support its planning. In these models, there's about 4 gigawatts of offshore wind selected in the 2045 time horizon. And on the right, you'll see results from a paper that used the Reeds network. And what they found was similarly meeting the 25 gigawatt goal by 2045 only amounted to a 0.05% increase in system costs. So both models show that there's some relatively low cost to achieving offshore wind goals that the CC has stated. But I wanted to look a little bit more into the assumptions that were made around transmission that led to these conclusions. And so I designed an experiment using the Reeds networks that were used in the previous figure on the right. And so here we just model California with balancing authority level resolution on the left and a county level resolution on the right. And we run a capacity expansion meeting California's 8 MMT target by 2050 in this case. And so to walk you through this slide, on the left, we have optimal capacity. On the right, we have supply mix. The dark purple is floating offshore wind. The Reeds network, you'll see, has offshore wind in its resource mix, and the county scale resolution network doesn't have any offshore wind. Instead, we see a lot more solar, a lot more battery energy storage, and a shift from longer duration battery energy storage to shorter duration battery energy storage. And so this is an example where having this transmission resolution to conduct planning for California really makes a difference in our planning, can make a big difference in our planning targets. Trevor's going to take over now to talk more about the sector coupled network. I've only talked about the electricity system portion of the network, but you can check it out online. I think we wanted to stop for like a few minutes to give room for questions if anybody wants to chime in. Maybe we can do like 5 minutes of questions or a few questions.
I think there was a few in chat. But first, thanks for the presentation. Super
Yeah.
helpful. Um, Yeah, there's a few in chat from Tom Brown, your hero. Um, have you tried comparing the nearest data to OpenStreetMap? Maybe the conductoring is too heterogeneous in the US. Not sure.
Yeah, I've started, so I have a branch on Pipes USA where I'm bringing in the OpenStreetMap data. I I have not, no, I haven't done that comparison on clustered versions of the OpenStreetMap data, comparing it to the nearest network. So the nearest network, the way it's calculated, very because it's using that optimization-based framework, even let's say the OpenStreetMap network had perfect identical representation of line capacities compared to the nearest network because they're calculating that those network line capacities with that n-1 optimization based method, the network capacities are not equal to the sum of the line capacities that we typically use in the pipes of clustering algorithms. And so in the papers that were used to publish those networks, you'll see that it's like ranging from like 50% to I think 80% less than if you were to sum the line capacities between regions.
Yeah, I guess for the European model, we have like a default like 70% like buffer factor
Yeah.
to account for that n-1, and it'd be good to be able to reproduce that calculation that they're doing because they can hide all sorts of like shady stuff in those calculations. So I
Uh,
don't know. I don't know. I don't really know now how the narrow data set is made, but it might be interesting to try and reproduce it with the underlying data. But then you could get grids that are very different from one place to the other. They may have three bundles or different cross sections as well. So we rely on the European model on the fact that the conductoring is relatively homogeneous, and I don't know if that really applies in the US as well. So yeah, it's
yeah.
complicated, but thanks for the answer.
Yeah. Yeah. One challenge I've had when I was looking at the Highfeld data set, which I think is pretty similar to OpenStreetMap, I think some of the information is shared between the two, is that in some regions where there's actual like double circuit lines, like 500 kV double circuit, the nearest status, not the nearest, sorry, the Highfeld data set in the OpenStreetMap will just show like a single 500 kV line where actually there's like two that should be going between these regions. So I've only spot checked certain regions, but I agree it would be nice to do a comparison.
Cool. We got another one from Tom Brown and then also one from Carly Hagan. So we'll start with which climate-informed data are you using? It's a global data set that can be integrated into AdLife.
No, it's just a US data set. It's from the Pacific Northwest National Lab, the Go Deep data set. I think it's from the climate model. I'm gonna botch the acronym TGW something something something. Sorry.
Sure. I got a thumbs up from Tom. Carly asks, is there any integration of data concerning aging infrastructure, safety, or fire concerns?
Um, Aging infrastructure. So we have data from Puddle from the EIA on existing like plant build dates and their expected retirements, but we follow the assumptions of the Reed's model in terms of like retirement dates for different technology types. So no, there isn't data on like fire risk for, is that what the question was? Fire risk? No, we don't include that level of resolution because it's, I guess, the resolution of like the individual paths of these transmission lines within fire zones isn't included currently.
All right. Looks like that's all the questions you had. Unless anyone else has a late breaking question in chat, we can move into Trevor's section. Thanks again, Kamran, for your
Yep.
presentation. Take it away,
Uh,
Trevor.
Beautiful. Thank you. Um, Hopefully you can see my screen okay. Beautiful. Okay, great. Thank you, Kamran, and thank you, Catalyst. My name is Trevor Barnes. As Kamran said, I'm a PhD student at Simon Fraser University in Vancouver, and I'm going to talk about the sector coupling side of Pipes USA. And just to acknowledge my funders is Mitex and Generac, who've been funding me on this project. Any views expressed do not necessarily represent the views of those organizations, though. So I'll cover firstly what I mean by sector coupling and why we'd want to do it. Then I will spend most of the presentation going over what data we've actually ingested into the model and how these sectors are represented. And then finally, I'll give some example results of what you can use the model for. So the motivation is really when we talk about like net zero targets, that includes the entire energy system. So if you look at USA net zero progress by 2050, the black line here is showing the historical emissions, the full energy system till I think 2023 is on this graph. And then the green and blue lines show the net zero targets from the 2015 Paris Agreement and then current day. And then the dashed lines are the 5, 10, and 15-year historical trends. And I know emission trends are not linear, but I think this conveys the point well that significant more progress has to happen to hit this net zero target. And if we look at where emissions come from in the United States, the electricity generation, which Kamran just talked about, that encompasses about 25%. However, these other sectors like transportation and industry and service sector, which have very close interactions to the electricity generation sector that also have to be decarbonized. So when I am talking about sector coupling, I'm meaning how do we represent these interactions to these other energy sectors and look at ways to decarbonize them to meet these net zero targets. So I'll first cover what in detail a little bit more and what I mean by these sectoral interactions. So I think it's important to explain that clearly before we just dive into the data. So currently, the power sector, everything that the sector coupled side of Pipes USA, it's built on top of the power sector representation. So everything that Kamran mentioned still holds true for the power sector representation in the sector coupled version. So what that means is we have fossil generators and renewable generators that come together. They generate power for the electricity sector. Then we can add building blocks in this. So we can represent other energy sectors. So we can say, instead of having just a single power sector energy demand or electricity demand, let's represent the residential and commercial, industrial, and transport electricity demands individually. And you'd want to do this because maybe there's benefits to trying to decarbonize one of these sectors before another, just based on seasonal or daily profiles. And then maybe we want to go a step further. We want to say, let's expose some fossil fuels into these energy sectors as well. For example, the service sector can use natural gas for their space heating demands. And then we can add in these other demand sources as well, such as heating and cooling and oil demand in the transport sector. So we slowly build one on top of these other. And then we can also represent fossil fuels quite well as well. So for example, the natural gas sector representing the generation capacity and the storage capacity of natural gas. And we can try to find how these sectors interact to look at new decarbonization pathways. And when I say interaction, I think it's important just to highlight what these interactions really are. So if we look at a single node in a sector couple version, we'll have the electricity sector. This will have storage, renewable generators feeding into it, fossil generators, and some sort of demand. And then we have our other end use demands as well, such as heating and cooling and our transport demand. And then maybe we'll add in some sort of other energy carriers. So in this case, natural gas, but it could be hydrogen or biogas or any other energy carrier. And then these interactions, these are the technologies that convert one of these energies into another. So for example, between some sort of gas and electricity, maybe like a Goward pass will be an example of a combustion turbine, or if we're going electricity to hydrogen, that could be a fuel cell. And capturing these interactions, really what I say when I say interactions, I mean capturing these different energy conversion technologies. And we can do this for all the energy sectors. So EV charging and air conditioning and heat pumps and furnaces. And all these parameters, or all these technologies, have techno-economic data and supply-demand constraints associated with them. And we can use this to try and identify these new pathways. So with that said, I'll start going into what data we're actually ingesting and what these different sectors look like. So I'll first start with the service sector. So service sector represents the residential and commercial industries. They are treated separately, however, they share a lot of similar demand, or a lot of similar data sources. So first up is the demand. So we take this from the NREL, Comstock, and Restock data sets. These are bottom-up synthetic data sets, and they represent electricity, space heating, water heating, and space cooling demand, and they provide pre-aggregated demands at state level and weather zones. So we ingest state level energy data, and on this left-hand chart is showing for a single state daily resampled energy demand profile for each of those four energy carriers. And on the right-hand side does show that we do pull in hourly level data. The nice thing about this data set is it captures really well in good detail the significance of the energy difference between these sources. So for example, space heating, as you can see in the left-hand chart, is 5, 6, 7, up to like 8 times more than electricity demand during the winter months. And capturing these significant differences is really important. So these data sets are used there. They are locked to a 2018 year. So to account for that, what we do is we scale this data against the annual energy outlook. So we will take the profiles that we just saw on the left-hand side, and then if we're doing a study in the future, we will calculate the difference between 2018 and 2030 or 2040, for example, and we'll just scale the magnitudes up. So we use the EIA to forecast this energy demand. But the profiles remain the same from the Restock and Comstock data sets. What the service sector looks like is shown here. I know it's a lot to take in, but it's pretty easy to break down. So at the top level for each node, we have 3 primary energy carriers. So one is generate electricity. The next is state level gas and state level oil. The primary energy carriers of gas and oil, they are tracked at state levels, and we'll talk about that later, why that is. And then electricity is tracked at a node level, as Kamran presented on. These can be used to meet our 4 end-use demands. So the first is electrical. This can be lighting demand, washing machines, this kind of stuff that are already electrified. The next is space heating. This can be met through electric, natural gas, oil, furnaces, or heat pumps. Space heating can be met through heat pumps or air conditioners. And then water heating can be met through gas, electric, and oil storage water heaters. And giving the model the option to use different fuels allows it to decide what fuel switching should happen. So maybe it's more beneficial to electrify one of these end uses. Maybe it's more beneficial to electrify the residential versus commercial, or maybe it's better to electrify a different industry completely. So we allow the model to choose these end use demands, or end use capacities, sorry, to meet these demands. Each of these technologies, such as furnaces and heat pumps, they all have capital costs, fixed costs, variable costs, lifetimes, efficiencies, and existing stock estimates. These are pulled from 3 different EIA sources. So the first one, the building sector, plants and equipment costs and efficiencies. That's the big one we use that approximates these a lot of these parameters into the future. We fill in some of that data with the energy outlook. And then for existing stock, we estimate that based on the residential and commercial energy consumption surveys. The last thing I'll note on the service sector side is for the heat pumps, there's 2 types ingested. One is air source heat pumps, and the second is ground source heat pumps. In this chart, I just show the coefficient of performance over 4 different load zones, shown the gray lines, and then the blue is the average between them. And we use the same methodology that Pipes Europe uses. So we pull in the same weather data that Kamran presented on, and we use Atlight to process that. And then based on a user-defined set point, such as I want 20 degrees C indoor temperature, we will calculate the coefficient of performance. So there are these two different heat pumps available to the system. Next up, I'll talk about the transportation sector. So there are 4 different modes of vehicle transportation modeled. So one is light duty, medium duty, heavy duty, and buses. These are shown in these 4 figures, A, B, C, and D, respectively here. These figures show for a single state the charging profiles, so load on the grid of each of these vehicle modes. So the gray bars show the daily profile. So there's 365 gray bars, and the blue is the average. We ingest this data from the NREL EFS study, and this will give state level charging profiles as shown here for a couple historical years and then select years into the future. We take the profiles here, and then again, we pair them with the energy outlook to get future demands. So for example, if I want a 2035 study, I will take the annual energy here, shown by the AEO, and pair it with the demands we saw on the previous slide. We then expose 2 different vehicle modes to the system. So again, we bring in electricity and fuel oil at the top, and then the model can decide what to invest in to meet light duty, medium duty, heavy duty, and bus vehicle demand. Much like the service sector, all these technologies, they have capital costs, fixed costs, variable costs, lifetimes, efficiencies, and existing stock estimates. A lot of this data comes from either the AEO or NREL EFS study. And 2 final notes on this. So one is just explained on the vehicle demand. However, we also have non-vehicle or non-road vehicle demand as well. And that includes marine shipping, passenger rail, freight rail, and passenger air. And those annual demands are taken from the AEO as well. These do not currently have the decarbonization options. We don't have anything modeled in terms of sustainable aviation fuel or anything like that. Right now, they're included simply for emission accounting purposes. So if I want to hit a 2035 target, we still have that demand modeled in to make sure we capture any emissions associated with this non-road vehicle demand. And then upcoming in the future, we'll be adding those decarbonization options. Moreover, our demands are all in units of final traveled units, so vehicle miles traveled, passenger miles, this kind of thing. And the idea there was to model that, and those values are taken from the AEO. So in the future, if we wanted to explore how to do mode shifting studies, it would be an easier path forward to explore those research questions. Next up is the industrial sector. So the demand here is a 4-step process. We first pull in this data set from NREL, which is the United States county level industrial energy use. So this will give at a per county level and per manufacturing or industrial sector, sorry, so by NAICS code, the annual energy demand per end use at a county level. This is a bottom-up model. However, it's from 2014, so it's a little old now. So we calibrate this against the latest manufacturing energy consumption survey from the EIA to get more to approximate current day energy demands a little bit better. And that methodology I take right from this NREL industrial energy tool study. So I didn't develop that calibration methodology. So that study goes over it well. So at this point, we will have annual energy demands at these large geographic scopes. To get energy or industrial demand profiles, we then pair that with EPRI's load shape library. So this will give hourly load profiles for a couple different end-use fuels, such as electricity and heating, at an hourly resolution. This is not by NAICS code, though, so it's a little bit coarse. However, I had quite a bit of trouble finding industrial energy demand profiles. So this is kind of the best I could come up with. So this will get us hourly load profiles from the industrial sector per fuel. And then again, if we want to scale that into the future, we use the AEO energy demand projections it's important to know at this point, so the previous demands for service sector and transportation sector, those are disaggregated based on population, if we have to disaggregate. For the industrial sector, we disaggregate based on the original county level industrial use data set. So this will capture where demand is actually happening for the industrial sector. So we do capture these spatial differences between where like service demand is happening and where industrial demand is happening. And that's what these heat maps are showing, just where for these 4 different states, where the industrial demand is occurring. Much like the other sectors, the technologies all have capital costs, fixed costs, variable costs, lifetimes, efficiencies, and existing stock estimates. The industrial sector currently is pretty coarse, I would say, in terms of what exists for future decarbonization scenarios. So we only have the 2 end-use loads for electrical and heating, and right now they're not disaggregated by industrial type. It's just one aggregated industrial demand. So we don't have like demand for steel manufacturing versus agriculture or whatnot. And moreover, the options to decarbonize right now are just based on gas furnaces, coal boilers, heat pumps, and electrical direct electrification. In the future, there will be interconnections to look at sustainable supply chains for that. And existing stocks are estimated from the Manufacturing Energy Consumption Survey. And finally, the last sector just to talk about is the natural gas sector. So natural gas is modeled in detail, and it's modeled at a state level based on data restrictions. So if you think of at each state, we have the central gas accounting bus. And then there are 3 main components attached to that bus. So one is the actual processing capacities. That is at a plant level, how much capacity can be injected into the gas system at any moment. So we pull that in. The next one is underground storage capacity. So at a unit level, what underground storage options exist for natural gas, and we do respect those operating limits as well. Line pack is estimated based on this high-field data set, and that is just geolocated natural gas pipelines, and then I make assumptions on diameter and operating limits to estimate line pack availability at a state level. So those are the main components at the state level. Trade between each state is allowed, so I pull in state level capacity limits, and then the flows between each state are endogenously solved for. And then if you have a region outside of your model scope, so for example, if I'm modeling Washington and I want to trade to Canada and British Columbia, we do pull in some boundary conditions there. So we have the actual pipeline capacity, and then as the user configurable option, if you want to like match that historical weather year imports and exports into and out of that region. And that just sets a boundary condition. If you have a province or a state that is heavily reliant on importing or exporting, just making sure to capture that we can do as well. And that's a toggle that can be on or off. The last thing to mention in the natural gas sector is we do also track methane leakage. There's an option to do that as well. So based on a user configurable leakage rate and global warming potential for every unit of natural gas injected into the system, we can also track the amount of methane released, and that would count against your allowable carbon budget for that year. Okay, I know that was a huge information dump. I'll just go over what some example results look like. So I'll just show some calibration results for the Western interconnection. This is run at 4-hour resolution. So 33 zones across the Western interconnect. So first up, I'll show what some state level emissions look like. So the blue is the actual energy system emissions, and the orange shows what actually happened in 2018 for emissions release. So we can see at state levels, we are pretty close, which is really encouraging. And that's really important because as you implement like emission policies, you want to make sure you have a good starting point if you're looking from a reduction in levels. So we are at like a fairly good starting point. For each of these states, sorry, you can dive down into like energy consumption trends or emissions by each sector as well. So it's showing energy consumption in California for that same year. So again, blue is actual, orange is modeled. So again, we are fairly close in matching some of these, and we're never going to be perfect since this is an optimization model, but just we're in the correct ballpark, I would say. And then for each node, you can also go in and look at the actual production results. So this is just showing residential sector for the system. So at each time slice, you can see how the total energy is being met. So that includes space heating, space cooling, electrical, all that. So all these options are exposed to you. Moreover, oftentimes for these energy system models, there's a lot of moving parts. So you want to be able to benchmark these against other energy flows. So places like the EIA and Lawrence Berkeley, they will put out Sankey diagrams of how energy is flowing around the energy systems. So this offers we can mimic that as well as shown here. So it's an output from that model, from our model. So we can look at like energy services and rejected energy and just how this energy is flowing through the energy system as both a validation tool and also a data exploration tool. So just to wrap up here, so what the model is good at doing right now, it can pretty well do near-term energy decarbonization pathways. When I say near-term, I mean basically anything does not include hard to decarbonize industries, such as industrial demand and like non-vehicle road transport. And that's mainly because there's no hydrogen integration yet. That's coming. So evaluate near-term, probably like 2035-ish, based on your research question. The interactions between the existing sectors, I think, is modeled quite well, as shown by the validation, and the natural gas representation, looking at specific results on storage levels and natural gas prices. We're matching them quite well. And then, yeah, the biggest thing for upcoming work is the hydrogen integration, and then figuring out where to get better industrial demand for. I think that's a bottleneck right now to create those sustainable supply chains. And last slide here, just to wrap it back to Puddle and Catalyst. So how is Puddle and Catalyst integrated into the Pipes USA sector side? So all the data that Kamran went over, we ingest all that into the sector side as well. It's fundamentally the same model. And so that includes things like the AEO and generator locations and whatnot. And then the other big thing, I think, is the archival of energy data. So probably a lot of people have seen the panic of some energy sources going away in the States particularly. So getting backups of some of this data has been really critical to me to make sure some of the data I'm relying on does not go away, but Puddle has archived a bunch on Zenodo already. So it's been like a little bit of a relief for me to make sure, like, if all of a sudden my energy consumption surveys go away, they still exist via Catalyst. And yeah, that was my presentation. Thank you, everyone.
Very cool. And thanks for the shout out. I was archiving some of the consumption surveys and be like, I wonder where this is going. But I'm glad you're making use of it. I think Tom has a comment on there being a NREL data set with some industrial data. Just
really
for your information. I don't know if there's
cool.
any specific questions. I don't see any in chat, but if you have a question, feel free to shout out. I see a question in chat from Brett Dolter. Are you thinking of integrating Canada to a greater extent?
Yeah, that's a great question, and maybe I can jump in there since I'm from Canada. Yeah, so when I was originally starting my project, I was originally looking at Canada pipes and models. However, there are a few different Canada pipes and models currently existing. So one by like the Canadian Energy Regulator. There's one by Natural Resources Canada. I think there's one kind of that's been in development by CanMed Energy as well. And the big holdback from that was it's really hard to get spatially resolved energy data in Canada compared to the States. And you even see it, I think, in these models because they don't release their data or code necessarily, but a lot of times they're like locked to province level resolution. So it's been kind of hard. So I have had like discussions at conferences and whatnot with some of these people developing the Canada models. So it'd be great to in the future. I think there is a lot of opportunity there, but it's not on, I think, the immediate timeline, at least from my side.
Hopefully that answers your question, Brett. Eli Gold has a question. Do you have a way to translate res stock and com stock profiles to other weather years?
That's a great question. The short answer is no, I don't. The so the pipes of Europe models, they have a process to estimate heating degree days, I think cooling degree days as well, based on the error 5 data. I did go through that process, and when I compared for 2018 data, I did notice there was a little bit like not crazy differences or anything, but there were some differences between the res stock, com stock, and the at-light approach. And I'm not saying one way is better than the other because the res stock and com stock are synthetic data sets. I've seen res stock and com stock used in other USA energy models, so that's why I went down that route. But to be able to get kind of weather independent, you'd probably have to go follow the pipes of Europe methodology of using at-light to estimate the heating degree days, cooling degree days. That's a great question. So yeah, so that is a limitation. We are locked to 2018 weather profiles.
All right. And one more from Molly Blundell. Coming from a consumer advocacy and EJ perspective, are you considering the high expense of creating green hydrogen and the immense safety risk of hydrogen blending projects? These factors have led to a lot of contention with PUC dockets in many states.
Yeah, another great question. Oh, sorry, Kamran, do you want to interject? No. That's a great question, and it will need to be considered when hydrogen integration happens, since no hydrogen integration has really happened from the sector coupling side. I haven't considered that yet, but it will need to be considered in some perspective. But Kamran, if you have anything to add.
Yeah, just saying that in terms of, I guess, down the same vein, my group does a lot of research on air quality and mortality from pollution. So in the coming year, it's likely we have a postdoc or somebody working on integrating pollution mortality within the model as well.
I think that's all the questions in the chat, unless people have any late breaking. Oh, from Forlin Cifuentes. Maybe I missed it, but are the res comstock data regional or state level?
Great question. So we can pull them in at different resolutions. So you can do by weather years and whatnot. I pull them in at a state level resolution, and then I disaggregate based on population density. So res stock and comstock will provide pre-aggregated state level. So that's what I ingest.
Very cool. Okay. Well, I think we're wrapped up here. Thanks so much, Trevor and Kamran, for presenting on your work. And thanks to everyone else for being engaged and asking questions. Yeah. I think you are all free to leave, though I guess if you want to ask more questions, feel free.
Thanks, everyone.